So here we'll look at the carboxylic acid derivatives. We'll briefly cover the nomenclature and physical properties, and we'll have a review of the preparations. But more importantly, we'll go through some named reactions and some synthesis. So remind yourself that the derivatives, of course, are derivatives of this carboxylic acid. So we substitute the OH for species like chloride, in this case acid chloride, or the carboxylate, which is anhydride. You can see here we got a thiol instead of an OH, and so this is a thiol ester. And of course here the nitriles, interestingly enough, are also thought of as carboxylic acid derivatives. Melting points and boiling points are quite similar, except for the amides. The primary and secondary amides, to be exact. Why? Because they do have hydrogen bonding. A tertiary amide will not, because the nitrogen, of course, is flanked by two R groups. So we'll look at the direct and indirect conversions to acid derivatives. So we'll be looking at acid chlorides, followed by esters, followed by amides. I think somewhere in there we've also missed out on anhydrides. So herein you can see exactly what we call an acyl group with the substituents. Under basic conditions, of course, you will see that we'll have this mechanism where if we have the harsh base, we can just simply add to give us our alkoxide derivatives, followed by elimination. This elimination of the leaving group results in an addition elimination, i.e. a substitution reaction. We've already seen that aldehydes and ketones do not have good leaving groups, and so therefore the product is adding an addition across the C double bond O. Realize that for both secondary and primary amines, the carbonylamine that is generated is unstable, and so dehydration takes place to give you imines and enamines. On the other hand, this would be a hemiacetal with an alcohol, and we can further, with more alcohol, generate acetals. Mechanisms are quite basic. Mechanism, the basic event, of course, addition and elimination with the substitution. But with weaker nucleophiles, then of course we're going to need the aid of a proton catalyst. The reactivity is affected mainly by our leaving group, and we'll discover some resonance and induction as well. So here you can see the basic event. Quite simply, we've done this before, again and again and again. Quite simply, we just add the nucleophile to the electrophilic center to give us our tetrahedral alkoxide, which collapses to generate our leaving group. The net result is substitution of our leaving group by the nucleophile. On the other hand, if you have a weak nucleophile, then of course we need the proton catalyst. So the proton catalyst will activate our carbonyl. So it's protonation to give us our activated carbonyl, followed by attack of said activated carbonyl. So the activated carbonyl is now our electrophile. And of course, here's our weak nucleophile. So nucleophilic center, electrophilic center, to give us our tetrahedral intermediates. So protonation, attack, to give us our intermediate. Now we have a proton transfers onto our leaving group. This makes our leaving group much more better, much more efficient at going. And so once this tetrahedral intermediate collapses to give us our pseudo-carbonyl, we end up eliminating our leaving group, and we have a precursor to our derivative. As far as leaving groups are concerned, you can see that the chloride is a very stable base, i.e. a very good leaving group, and so the acyl chlorides are the most reactive compared to the amide, which is a very poor leaving group, and so our amides are the least reactive. We can summarize it quite simply, because if you look at the acyl chloride, not only do we have a rather good leaving group, but of course, yeah, inductively, the chloride is rather good, and so it creates a higher electropositive center, i.e. this carbon is more electrophilic. The resonance contribution here is not very good because chloride is highly electronegative, and its propensity to donate electrons into this carbon-chlorine bond is very poor. On the other hand, if you look at the amides, this is rather good, so this is rather significant contributor. The amide is also a very poor leaving group, and so the acid chlorides therefore becomes the most reactive acid derivatives, and the amides are the least reactive. We can look at the specific reactions, and we saw all of these will react with an acid chloride. But then when we look at these acid derivatives, we got to be careful of how we view the reactivity, because this is decreasing reactivity, i.e. poor leaving groups. So if you think about this as an acid base, then of course, if you compare the carboxylate and react it with the amide, then of course, this is a carboxylate. This amide would be a leaving group, and it's a stronger base than the carboxylate. So this will never happen. On the other hand, if you look at the amine with the anhydride, then of course the alkoxide, well this time around it's not an anhydride, it's an ester, but the alkoxide is a weaker base than the amide, so of course this reaction will take place. We have here, for example, a question which will react fastest. And of course, you and I know that the acyl chloride is the species that's going to react fastest. But a question that I would ask in an exam is, what is the order of reactivity, starting with the most reactive? Think about that, we can talk about it during our discussion sessions. This mapping, by the end of this work, should be in your head. And so I personally do not put this in memory, but yeah, with practice, you will find it easier to remember. So for example, here, when we look at something like this, you and I know that oxygen is a weaker base than nitrogen. So this is a weak base, strong base. And so this reaction will not happen. On the other hand, you can see the difference between these guys here, yeah? And so these guys will definitely happen, okay? Because these are very good leaving groups. And that leads us to this. When you look at the first set of reactions that we're going to do, we're going to look at reactions that do not require catalysts. These are the acid chlorides and the acid anhydrides, because they consist of very stable, very good leaving groups. The acid chloride itself is quite easy to make. You react thionyl chloride with carboxylic acid, and realize it is the same reagent that you use to convert alcohols to alkyl halides. However, in this case, you need a bit of base to mop up that HCl. And in this case, we're going to use some pyridine. You can see that in all these cases with the acid chloride, we're going to need a bit of base, because the hydrogen chloride will be your byproduct. In the case of the amines, we use two modes of amines. One will act as a substituent, and the other one will act as the reagent that mops up the excess hydrochloride. This mechanism here is quite efficient. Why? Because we have the sodium salt of the carboxylate, which will react with the acid chloride. It's a basic event. And of course, we end up with our carboxylic acid derivative, which will then eject our leaving group to give us our product. Very straightforward. In this case here, our product is the anhydride. Here, on the other hand, we're looking at a neutral event, and, well, this is still our electrophile, and the carboxylic acid is our nucleophile. Of course, this is our nucleophilic center, and this carbon is our electrophilic center, and so the attack will occur to give us a tetrahedral intermediate. However, you can see that some proton transfers will occur, followed by a collapse of that species to give us ejection of the chloride, and then we have a precursor to our anhydride. Again, we're going to need a bit of base to mop up the excess HCl. We can prepare these anhydrides cheaply by dehydration. For example, 2 moles of the acid with heat, we will get the anhydride. Realize that if we have these cis diacids, then the reaction becomes much more efficient. So here, for example, we have phthalic acid to give us phthalic anhydride, and maleic acid to give us maleic anhydride. It has to be cis because in the case of fumaric acid, which is the trans acid, the proximity of the acids are too far away, and so this will not give us the dehydration to form the anhydride as we want. The most efficient way, as we saw from the mechanism, is the reaction of the carboxylate with the acid chloride to give us the anhydride. What's wrong here? Could someone tell me? The reactions of the acid anhydride is quite similar to the acid chloride. You can see we have alcoholysis, we have hydrolysis, and we'll end up with, in this case here, we end up with the acids, we can end up with esters, and here we got amides. Realize that we do the same thing as before. We need some base to mop up the excess acids, and in this case here, we need the excess base to mop up the excess acid, and it's isolated as the ammonium salt. Here we have a play with nomenclature. I want you to have a think about this one, and I'll pause right here, and I expect you to pause, and then we can discuss this during our lectures. The Fischer esterification is our first named reaction, terribly important to us, and so we'll look at that in more detail. We can also react these acid chlorides or anhydrides with alcohol. We've already seen those nucleophilic substitution reactions. We've already probed the biovillager art from previous chapters, and of course we've looked at the carboxylate anions with alkyl halides to form esters in organic 1. So the Fischer esterification, we have an acid with an alcohol, the alcohol of course being quite cheap, so we can use it both as solvent and reagent, and we literally want to have a desiccant or a beanstalk to get rid of this water byproduct, and this will drive the equilibrium from left to right. The mechanism, of course, is something that we've seen before, or if not, it becomes intuitive to you, because you can see that we start off with a protonation to activate that carbonyl. Then, of course, we attack with the nucleophile in this case being an alcohol. You can see that this is your nucleophilic center, hitting the electrophilic center. The tetrahedral intermediate will then undergo proton transfers. That's followed by elimination of water. So protonation, attack, proton transfers, elimination of water to give you the precursor to your acid. Here we have intramolecular esterification. You can see that with a bit of acid catalyst, when you have a hydroxy acid, in this case here we have a gamma hydroxy acid, then you end up with a cyclic ester called a lactone. So we have a gamma lactone, which is a 5-membered lactone. Here we have a delta lactone, which is a 6-membered lactone. The mechanism, of course, you start off by activating your carbonyl. The molecule, you can see, has both a nucleophilic end and an electrophilic end. So here's our nucleophilic center, here's our electrophilic center, and so the attack will occur to give us a tetrahedral intermediate. Tetrahedral intermediate has to have a proton transfer because we realize that the water will be a leaving group. So there will be a proton transfers, and now you have, after the proton transfer, an elimination. Elimination of water to give you the precursor to your lactone. Reactions of these esters, of course, similar to what we've done in the past. However, realize that we need harsher conditions because these OH is a poor leaving group, so we either generate some type of, the OR is a poor leaving group, so we generate the alcohol or the alkoxide. So in the acidic condition, we're going to have to find a way to proton transfer to eliminate an alcohol. In the case of the amine is a stronger base, and so the elimination of the alcohol is a little bit better. So we can look at the hydrolysis. Hydrolysis on the acidic condition or basic conditions. This hydrolysis is called saponification. You can see that we need an acid catalyst. So of course what we do is we protonate to activate our carbonyl, and then of course now we attack the ester with water. This is the activated ester with water, and then after this tetrahedral intermediate is obtained, we have a proton transfer. The proton transfer will realize this alcohol as a leaving group, which we can eject quite simply to give us the precursor to our acid. Could you work on this one for me? So to summarize, we have our ester we can saponificate on the acidic conditions, basic conditions, and you can see that we can do an alkoxide swap, R-, for R-. We can react with amines. We've come across reaction with Grignards before, and you realize that these Grignards are obtained from esters because this tertiary alcohol is obtained from esters because two R groups of the said tertiary alcohols are the same. And of course, we can also react with lithium aluminum hydride, total reduction to give you the primary alcohol. And of course, partial reduction with DIBA will give you the aldehyde. In nature, these fatty acids are quite ubiquitous. You can see that we have the acids followed by a long hydrocarbon chain, whether it's saturated or unsaturated. So this is, of course, a unsaturated fatty acid. And this is a saturated fatty acid. They're usually wrapped up in glycerol, glycerol triacyl glycerols, which are type of esters. So what we can do is perform saponification with a base, i.e. under basic conditions. We have a glycerol byproduct and of course sodium salts of these fatty acids. These sodium salts of these fatty acids are what we call amphiphilic because we have this long hydrophobic end and the hydrophilic end. Yes? And when they assemble, then of course you can see that literally they assemble in a micelle. The micelle, of course, has a outer shell which is hydrophilic and an inner shell which is hydrophobic, and the hydrophobic center can hold particles such as what we have when we use it as a soap. Amides are, of course, the least reactive of our carboxylic acid derivatives. This is quite new to us, direct synthesis of carboxylic acids using DCC. In the case of the reactions, and most of these we're familiar with, but not the decarboxylation reaction called the Hofmann elimination. But we've come across dehydration to form nitriles in the past. So here, for example, a quite simple synthesis, not as efficient, but we react the phenyl chloride with a carboxylic acid to form the acid chlorides, which we can then react with various amines to give us our amide. Remember, you use 2 moles of the amine, 1 mole to substitute, the other mole to mop up the acid. Here are some more interesting ways of synthesizing amides. One way is, of course, reacting the carboxylic acid with ammonia to give you the ammonium salt. On heating, you get a dehydration to give you the primary amide. Not very efficient. On the other hand, if we react the acid with a primary amine in the presence of DCC, then of course we can get a secondary amide. The DCC, of course, is a dehydrating agent and also promotes amide formation and is called dicyclohexyl carbonate. So of course, the answer should be really D. So the reactions of amides, of course, they're summarized like this. We've seen these before. Hydrolysis. These are conditions of much harsher. Lithium aluminum hydride we've seen before. This is the deoxygenation to give you the corresponding amine. And of course, we can use a desiccant to give you the nitrile. And of course, here we have the Hofmann elimination, which we'll cover when we do amine chemistry. But please be familiar with it. Reaction like this shouldn't be a problem to us because you can see that we use phenyl chloride to give us the acyl chloride, followed by substitution of the amine to give us an amide. So we should be looking for an amide, and then we can count our carbons to figure out what the answer is. Pause it, please. Similar sort of system here. Now we're playing with nomenclature. Remind yourself that the species is dominated by the carbonyl group. And so what we need to look at now, these so-called cyclic amides, which we call lactams. You can see here we have an amino acid. It's a delta amino acid because there is an amine group on the delta carbon. And so with that, we form a 6-membered ring lactam, a delta lactam. You can see, for example, of course, 5 and 6-membered rings are healthy, but in medicinal chemistry, these are very widely used, and these are beta lactam. They got alpha carbon, beta carbon with the amine, and so we end up with this beta lactam, so 4-membered cyclic amide. Why don't you go ahead and research these beta lactams and then you can answer these questions and we can talk about it in class. Some other esters we should talk about, these that belong to the phosphoric acid. You can see phosphoric acids, of course, yeah, got the phosphate group. Remind yourself that phosphorus itself has d orbitals available to it, and therefore, why we can expand beyond the octet. Herein you can see that the phosphorus has some alkoxy groups attached to it, and or OH groups. Nitriles are interesting species because nitriles, yeah, do not have a carbonyl but have the C-triple N, and they're still acid derivatives. Most of these reactions, of course, you've come across when it comes to the preparation. The hydrolysis you would have come across before as well. And so the only thing that's new to us is the Grignard and the reductions. Yeah, it's sort of new, and so we'll look at this carefully. You can see here, for example, the bimolecular attack to give us a nitrile. You can see desiccants to give you the nitrile. Here, this is a coupling reaction, of course. Here, you can see another coupling reaction to give you the cyanohydrin. So the cyanide quench, give a cyanohydrin. And remind yourself what we can do with these nitriles. We can convert them into amides, so reduce them to amides, or we can hydrolyze them to acids. And we will introduce some other reactions that we can do with these nitriles. So here we have the hydrolysis on the acidic conditions and on the basic conditions. The mechanism, of course, goes via this imidic acetotonol. So what you got to do is go ahead and do this reaction for me, or the reaction mechanism for me, and of course the imidic acetotonol will tautomerize to give you the amide tautomol, which is your desired tautomol, the more stable form. You can see here, yeah, we can react with Grignard, and Grignard quench will give you this imine. Of course, the further quenching provide hydrolysis of the imine, i.e. the deamination will take place to give you the ketone. So this is your final product. Lithium aluminum hydride, of course, will give you total reduction to give you the permanent amine. What would DEBA do? And why don't you go ahead and do the mechanism? Realize that Grignard can only go once into the nitrile because this nitrogen is less electronegative than oxygen. So we will not go in twice because this carbon is not as electrophilic as the carbonyl or as electrophilic as this carbon. Summarize, we can hydrolyze, we can partial reduction, we can do a full reduction. What was missing there, of course, was the reaction with the Grignard. Here, of course, you can see that we have hydrolysis. We have a 1, 2, 3 carbon. So, of course, that would be propanoic acid. I think we've seen this before. So, with our synthesis, we should realize by now, the question that's always asked is there a change in the carbon skeleton? If there is, then of course you've got to look for coupling or cleavage. Is there a change in functional group? You know that now that we covered acid derivatives, our main focus will be that of the derivatives. This is now familiar to you, and we learned this, for example, root in organic 2, but this root here we already know in organic 1. Stuff like this, for example, hydrolysis, various conversions all the way down. So this shouldn't be a problem as far as memory is concerned, because we will practice. Herein, for example, you can see increase in oxidation level from left to right. We've already seen how we can do these conversions from left to right. and from top to bottom and vice versa. The only thing that's new here is, of course, the derivatives. All of these coupling reactions we're familiar with. These are new. Everything else is what we've covered before. So here, for example, we have a Grignard carbon dioxide quench. Here, of course, we have the cyanide by molecular event to give us the nitrile. Hydrolysis gives us the acids. Something like this, of course, you can easily answer in an exam. We would also like you to go over this as quickly as possible. Yeah, some interesting roots, for example, like here. And of course, some interesting synthesis procedures, like from here to here, and from here to here. You can see that there's a number of couplings in this one, here and here. I think this is the end of the synthesis. We're just going to show you some pharmaceuticals. Here, for example, aspirin, yeah, and acetaminophen. Literally, we're taking advantage of the protecting capability of the acetyl group. So, for example, this proton is quite acidic, the phenolic proton of salicylic acid, and so we're protected with a bit of the acetate, yeah, and of course that will give us aspirin. Here, for example, yeah, we have this very basic amide, amine. So what we do, we're protected to give it an amide. The nitrogen is now non-nucleophilic, non-basic. It's now protected. And now we have, yeah, Tyler. In biology, biochemistry, we have this species called acetyl-CoA. And of course, this is nature's way to provide an acyl group on any biomolecule. The leaving group, of course, nature's leaving group is the thiol-CoA itself. We'll talk about this when we have our discussions in class. So this is the end of our work, and we'll review all this material when I see you then.